Here I'm asked to sketch a graph of this function. First thing I'm going to do is set up my force fields. I've got -3. And here the force field turning on. I just got a funny look from Mr. Butterworth about that. And then we've got another one at 2. Another force field energized. Then I'm going to make a table. Okay. Starting with my points below -3, maybe, I don't know, -5 and -4. That seems pretty good. If I plug in -5, I'm going to end up with positive 3.5. If I plug in -4, I'm going to end up with positive 3. So -5, positive 3.5, and -4, 3. If I were to draw this line, so going to left is easy, it goes like that. Totally missed my point, but that's okay. Going to the right, it's going to go, hit the force field and stop. All right. Middle part, I'm going to use red for this, and 2x minus 1. These have to be points between -3 and positive 2. Maybe 0, I like using 0, and 1 is also pretty easy in there. So 2 times 0 is 0, minus 1 is -1. And 2 times 1 is 2, minus 1 is positive 1. All right, so I've got 0, -1. And I've got 1, positive 1. This guy's tricky because he's stuck between two force fields. So if I go down, then say beep, pew, hit the force field. And then the other direction, I follow this line until pew, hit the other force field. Finally, I'm going to look at my points above x equals 2. This might be a point like, I don't know, maybe 2. No, it's not big enough. How about 3, or 4, or 7, or 20 billion? So if I find 3, if I plug 3 in for x, I get 3. Cool. If I plug 4 in for x, I get 4. Cool. 3 is there. 4 is there. You can graph all the way that way, no issue whatsoever. If I try to go to the left, all of a sudden, pew, force field. And now I can fill in my open and closed circles. Okay, at my -3 boundary, I'm going to have an open circle for just less than, and a closed circle for the less than or equals. Or greater than or equals, rather. My next one, I'm going to have a closed circle for the less than or equals, and an open circle for the greater than. Here we're looking at an absolute value problem, and the first thing that I notice is that inside my absolute value, I've got x minus 3. That means it's probably a really good idea to start my table off at x equals 3. My goal is to make the inside 0. Okay, a half times 0 is going to be 0. Cool. -0 is still 0. Plus 4 is 4. Woohoo! Okay, next thing I notice is that I've got a half out front. It'd be a really good idea if I kept the stuff inside the absolute value even, so that if I multiply by half, I get a whole number. So instead of going up by 1, I'm going to try going up by 3 and see if that helps. Okay, 5 minus 3, 2. -1/2 times 2, -1. Nice, no fraction. -1 plus 4, that's going to be 3. Right on. All right, let's try going the other way. If I go 1 minus 3, I get -2. Cool. Absolute value, positive 2. -1/2 times 2, -1 plus 4, 3. So we've got 2 points. Let's jump 2 more out to 7. 7 minus 3 is 4. -1/2 times 4 is -2 plus 2 is 2. I'm sorry, plus 4 is 2. All right, and then down to -1. -1 minus 3 is -4. Absolute value is positive 4. Times -1/2 is -2. Plus 4 is 2. Oop, that's the wrong point. And there's my very cleanly, nicely drawn absolute value graph. Please make sure yours looks better than mine. Mine looks kind of like Mount Fuji. Although I realize you may not have ever seen Mount Fuji. So ta-da, there's Mount Fuji. I think this is from Cars because that looks animated, and I think I saw that it was from Cars' website. Next, we're solving a system using any method. I notice in inspecting this that I have two coefficients that are of opposite signs but the same number. That suggests to me that elimination might be a productive method to solve this problem without causing myself too much pain. Let's see what happens if I add these two equations together. 3x plus negative 3x is 0. Negative 5y plus 4y is negative y. Negative 1 plus negative 2 is negative 3. So y is negative y is negative 3, which means positive y is positive 3. Okay, I'm going to plug this back in. So 3x minus 5 times 3 is negative 1. I'm going to add 15 to both sides. I get 3x is equal to 16. Means x is 16 over 3. Except then I learned that I couldn't actually add, and adding 15 to both sides to get rid of that is going to end up giving me 14, not 16, so that's 14 over 3. For number 10, I'm supposed to solve a system using any method, and I notice that I already have a y by itself. That suggests to me that maybe substitution is the ideal option here. Substitution. Okay, so I'm going to rewrite my first equation. 2x minus 3, I'm going to put a nice big bubble for whatever y is equal to negative 17. And in that nice big bubble, which we know is really parentheses, I'm going to include my entire thing that's equal to y, 4x minus 1, like a champ. So 2x, negative 3 times 4x is minus 12x. Negative 3 times negative 1 is plus 3, and that's equal to negative 17. 2x minus 12x is negative 10x. Plus 3 is equal to negative 17. Minus 3 to both sides, I get negative 10x is equal to negative 20, which means that x is equal to 2. Plug that back into this bad boy right there. Y is equal to 4x minus 1. Therefore, if x is 2, y is equal to 4 times 2 minus 1. Y is 7. For our first extension problem, we have to solve the equation written below. I'm going to distribute first. I get negative 8x and plus 12. 6x, 8x minus 5. 6x minus 8x is negative 2x. Plus 12 is equal to 8x minus 5. Okay, now I'm going to start combining some like terms. Probably add 2x to both sides. So I get 10x is equal to 17. X is equal to 17 over 10. And finally, I have to solve an inequality for my other extension problem this week. I'm probably going to start by moving x's to one side. I'd like to get rid of the bigger negative if I can. So I get x plus 8 is less than negative 10. If I subtract 8 from both sides, I get x is less than negative 18. There's negative 18, and if x is less than negative 18, we have to draw our arrow going to the left. And the last thing is I need to decide if this is an open circle or a closed circle. Less than instead of less than or equal to is an open circle. Thanks for playing.